Oh, yeah, we have time. No problem. So we have now the second presentation by Kim et al. The title is Statistical Decomposition of Coastal Surface Current and Sea Surface Height and Evaluation of Their Performance. Please, Kim.
Yeah, hi, Kim. I'm from Korea Advanced Science Technology, and I'm going to give a talk on decomposition of surface currents in coastal areas to get or convert to the surface height and back and forth. But it's still in progress, so I'd like to hear some comments and opinions. Primary work done by NLE in my school and cursed by Alex Kropov of NOAA and Mike Kushner in Oregon State University. The snapshot in the left-hand side this is from high-frequency radar drive surface current over west coast from San Diego to the southern Washington state. So you can see different color is followed by magnitude in 6 kilometer resolution hourly snapshots. And primary data in Oregon State areas. So motivation of this work, high resolution in kilometer and hourly data are available from measured by high frequency radars. And it will be very useful if we can convert to the coastal sea surface height at a similar resolution for the evaluation or validation, the observation of obtained from upcoming satellite missions given by the first speaker and the SWAT and other missions. So one of the problem that we have, if you have surface current, is vector quantity, and how can you convert to the SSH scalar quantity? And also, if the upcoming missions provide sea surface height, whether we can convert to the sea surface currents or not. So that's the one of science question that we motivate by this topic. So in this talk we try to conduct a Helmholtz composition and wave vortex composition using the ROS simulation results. So we have SSH and surface current, whether we can convert back and forth, and how they physically consistent and also statistically consistent in that in the evaluation process. However, the wave vortex composition has a solution for isotropic and stationary process to decompose into balance and imbalance motion. So it has some sort of limitation also. It only decomposes into wave number domain, not the physical domain. So we presented Helmholtz decomposition can be another way to get the system side relevant quantity. So we'll present more detail. So as you might recognize, let's see. Entitled the Helmholtz decomposition can be done in the physical space, and you know, can do this one. You can do that in the physical space and spectral space. So in a given vector quantity, U and V component can be decomposed into a radial component called the stream function and divergent components and velocity potential. So given vector quantity will be clearly defined, uniquely defined in the stream function potential. As an example, the bottom here, diverging vortex in a space, you can decompose into rotational components for stream function and also diverging components, the velocity potential. So this is a more typical way to do, and you can do in the physical space, which means x, y, or temporal domain. If you have map, a stack of both map or time series, you can do that in the physical space, and also you can do that in the spectral space. And so If you help me to disappear, make it around the iris. It's fun. Not possible. Okay. Wave vortex decomposition only can be done in the spectral domain. So by incorporating the vertical buoyancy information when partitioning wave components, we call them unbalance, and vortex component balance motion can be quantified in the wave number domain. So the plot in the right hand side here, wave number space and spectrum. There are two lines here, the end of the spectrum. Blue indicates the vortex balance motion, and red in the unbalanced wave motion. But if you make a original data set, you have spectrum in the blue here and red one. But by this wave vortex composition can decompose into two different spectrum. For example, wave number or wave motion will be inertial gravity wave, internal wave, other azeotropic components, and also vortex motion, balance motion, typically has azeotropic balance. So we call the transition scale in this cross-section part, but this is one typical way, but it only can be done in wave number domain. And the characteristics of coastal surface current you may recognize in the Washington, Oregon state. We use hourly data for 2 years and plot the spectrum on the frequency domain. You can see clockwise in the red and counterclockwise blue. There are two different energy distribution, but I put it in the cycles per domain here. So 1 cycles per day means once a day, 2 cycles per day means twice a day. So you can see tidal energy and also near inertial peak and the clockwise direction. So coastal surface currents contain the tide and wind and inertial motion in low frequency. You may see below the 0.5 with 10 days signals here. So it has more driver, is a mixture of that, and also the process has anisotropy, which means U and V velocity may not be the same variance, it's not equal, and also may not be the non-stationary and inhomogeneous. So that means temporal lag and spatial lag may not be generate the same quantity in this domain. So we have some different characteristics of the physical process. So this is the given problem that we have. So we picked the Oregon State coast here, the domain for a numerical model, and it's over 40 to the 50, and we're focusing on the smaller domain in the coastal area up to 200 kilometers. But as we have entire bigger domains, so we can extend it from shore to the full 50 kilometers offshore. And the given ROM simulated data has 2 kilometers in hourly data, which is comparable to the high frequency data in this region, even though it's 6 kilometers in the observation though. But we are going to looking at how sea surface height and surface current can be relevant and how can we convert back and forth, but that's going to be one task. And also before that, I'd like to looking at how ROM simulate currents. It's comparable to the HF radar surface currents. So I just pick one single axis here, it's called D1, and we send the surface currents from ROMs and also the same axis for overlay on the HF radar here. So we have about 150 kilometers or so for the observations. The way to look at this figure is x-axis will be frequency for cycles per day, and the negative will be clockwise and positive counterclockwise rotational tendency, because UV velocity component has it clockwise, can be clockwise, and can be counterclockwise over time. So we decompose into two different directions. And y-axis will be cross-flow distance from 0 to 150 kilometer for surface current, and also domain, the ROMs has a more longer extent, but you can compare to the comparable location for 50 kilometer of a green arrow here. As I mentioned in the earlier slide, it's similar for low frequency variance and also tidal movements in cloud and counterclockwise, and also inertial motions and between K1 and N2. But you might see the cross-flow distribution. For example, inertial motion will be limited by coastal boundaries, so there are various will be used. This is the given operation, and also low frequency has coastal influence, so it has a more enhanced variance in near the coast compared to the offshore. So if you look at the raw simulation, if you only focus on the 150 kilometer, you might see similar tendencies to reduce the variance in high dimensions and low frequency. So we are going to use these currently raws in this rigorous. So we try to compose into system surface current from raws into the hammer decomposition and also wave technical decomposition. Wave technical decomposition multiple steps. You have to decompose into the stream function potential. Then you can decompose into balance and balance motion. So I'm going to present similar figures, and this is the wave number domain, and Y is a spectrum, and U, V, velocity separately considered here. So in this regional location has orange current will be more dominant, so V component will be dominant here. So you may see blue part will be a little bit more variance compared to the U, the red part. And as we have numerical simulation, we have buoyancy information. So I put it in also buoyancy spectrum, the green here. So given velocity, and you can decompose into T and psi in the wave text decomposition, and you can see stream function and potential components given by red and blue, and stream function will be much dominant in this region. And if you consider the stream function potential, sum that up, we can have a black one. So dominant feature will be stream function in these regions. And if you finally do the balance motion, so we can see the red part balance motion and the other one balance motion. So in this regional area has more balance motion dominance, and we do this our own way of kind of decompositions, and they have similar tendency, but not exactly the same spectral distribution. So the one thing I'd like to take apart is we try to do similar analysis for potential decomposition and how to decomposition in physical space, so whether they are consistent or not. And we may use this decomposition to make proxy for system heights. So we take a look at whether stream functions and SSH have some coherence and how they distribute over in space and frequency domain. So if you look at this top figure here, we make the coherence and try by the power here 0 to 0.5. So it's not that big, not like the 1, but if you look at frequency axis versus distance, you may see stream functions and SSH has quite relevant in the low frequency, which is just a big dominant region, and also some of inertial motions areas, but not all the areas. So we have some limitations to use the stream function. And also, if you look at only spectrum of the stream function energy, they have low frequency and also other inertial motion and tidal variance as well. So we just try to make an effort to how can we use the stream functions or relevant quantity can be as a proxy for system type, but there's some limitations, particularly the inertial motion band, and also SSD does not have inertial variance. So we may have to take a look back on what can we improve to get the system type information from surface currents.
2 minutes. Okay.
So this is summary. We try to look at the simulated observed surface currents, looking at the decomposition to get the balance and unbalanced motions. But wave vortex decomposition may not be applicable to coastal regions because isotropy, homogeneity, and stationary, and also UNV components has not its correlation. Also, the variances may not be the same. So we take a look at the another way we get thermal decomposition to get the proxy for SSH, and still in progress. So thank you for your listening, and I'd like to hear some of your comments. Thank you.
Yep. Thank you. So we have time for one question. A question? One, Alan.
Thank you for your talk. Did you check any wave current interaction, for example, near the coastal area? You are mentioning azimuthal because and the inertial oscillation, so it's process more related to wind stress change at the surface. Did you check any behavior induced by the waves in this area changing of the wind stress?
Not worried, but wave current interaction, when I referring that surface area wave with the currents may be right, but it's not the scale that we can look at as that interaction, but it's good comment that we might consider. Thank you.
Okay, thank you. And now I invite co-chair Luciana Fenoglio-Marche to take the floor. She's going to talk about ESA-ESRIN water level change from high resolution altimetry.
So good morning. So welcome to my presentation, which is about ESA-ESRIN water level change from high resolution altimetry. So what I would like to show in this presentation is what we are doing at the moment in Elbe estuary and Riva with Nadir altimetry. So what we have, so the goal of presentation was looking at what we can do and in this region, and we also tried to figure out what we can do with the next mission SWOT. So we have seen that it will be soon possible, but the concentration is on Nadir altimetry, and especially in the reprocessing and new retracker and new processing. For example, we use also fully focused SAR. So first of all, yes, I have to acknowledge my co-authors that are mostly from the University of Bonn. And we have also some collaboration with the Helmholtz-Zentrum in Gerstach, which is situated exactly at the point when the river becomes a river and is not anymore a tidal river. So they have a very high resolution model toward work with this, and we will work also with other models in order to understand the estuary and what we can see from space. So as I already said, the goal is to monitor a river to ocean continuum from space. This is something that we is related to what we are doing with coastal altimetry, but now coastal altimetry is going more and more to the coast and the internal of the inland water. And the estuary have the peculiar characteristic that they are not like river where you have no tide. You can observe for a long time, one day, without a lot of change. But here is we have is very dynamic and is particularly interesting to have a look. So the research question is how to exploit the new SAR, so it means the last processing that we can do with SAR altimetry, perhaps for the moment, and to look what SWOT altimetry can do, not so together, and to do better, and to have work together with SAR altimetry in order to get what we want. So one of the goal of the things will be to separate tide and discharge in the estuary, of course. We have a problem with the repetition, with time frequency of the time of observation of the instrument, and then go into salinity front and so on, but it will be for the future, and of course also extreme, as we already mentioned. So in my, I will first of all show the data that we have, so from the point of view of the altimeter, but also the model. And we consider the methodology, so we wanted to assess the accuracy and of our instruments altimetry. And then we will try to consider a model method where to separate the two, tide and river in the tide and river discharge. And I will show some result. So this is the region. So you see on the right part a very full of tide gauges and in situ measurement, Baltic and North Sea regions. This is the German coast, which is a very good place to study. If you want to stay in the ocean part, in the North Sea part, you have also the tide, and the other one you have a small tide, and you can sometimes forget, but not completely. So what we are looking at now at the moment is the Elbe. So here is the Elbe. You also have the same tide gauge, of course, but you have also a lot of GPS. So all the points that are here are GPS that we will allow you to do absolute positioning, but also this GNSS air that was yesterday explained some good results from Akan in the coast. So here I put also something that is very interesting and new and useful to work with, also for needle altimetry, also for people working in needle altimetry, is this concept of that is come out in principle for me, for working with SWOT. So you have a SWOT database where you have not only, we have the central line, you have the concept of reaches and so on, and we will also use already in the river with tide. So now we look more in detail what we try to do with the nadir altimetry. We would like to usually use 4 tide gauges. One is here in near to the estuary, and then there is another one nearby. So they are all located under the Sentinel-3 tracks, or Sentinel-3A or 3. So I consider 4 tide gauges, and I try to compare the accuracy of the data, of the altimeter data. And then we have other measurements that I told, and we have some model, as I saw here. So it's a region where we have a lot of data to work with. The method to compare altimeter and tide gauges was described by Jesus yesterday. So there are different ways of doing different. We get, of course, depending on the method, you can get different results. So I call them. So we have one, for example, that is the nearest virtual pass. That is, you consider the track that is in your river or on the coast, and you make a weighted average for the pass. You can also use another method that I call hydrocoastal, where this average you do for 20 kilometers. That perhaps you don't want to do this if there are a lot of variability, but it's good. But what I will use here, and what I prefer, is to looking at the track, and then to bin at the frequency that I want, and then I have time series that I will correlate with my tide gauges. So, and then we have to think about it. With correction, we don't apply, so we don't apply the DAC because in a hydrocoastal project, we decided not to do, and it's a good idea also to do that. So here is, I show you the standard deviation difference between this bin data, between a tie gauge, so one of them, they are ordered in alphabetic order. The Ottendorf was the one almost on the North Sea. The other one is the next one. And then when you go to Hamburg, you go to this one. So this is Glückstadt, and then Schulau is almost near Hamburg. So you see here a standard deviation difference which is evolving along the track. This means that depending on the point that you choose, you will have a different values. For example, here you have 2 meter accuracy, and here you have just 40 centimeters. So of course you say that you prefer to take the smallest values, also it is far away, but you could take this one. So this means that when we look at standard deviation different accuracy, you have to exactly to say where it is, how many points you use, and so on. Otherwise, it's a little bit not precise. And what the result that I show here I use the Air Console Samoza Plus normal processing, so the one for Salvatore processing. And I consider also the fully focused SAR. And in order to have things comparable, I process the fully focused SAR or the CLS, so this SMAP. We exchange the retracker, you use the retracker, this one, and the result. And you see that, we should use some statistic, that this Samoza Plus is performing very well, also in fully focused SAR, and we are happy about the result. But they are really very similar to Samoza Plus of Air Console. The only difference, of course, I could have processed also at 80 Hz here, but if we have fully focused, you can go until 640. This means that you can have a long track, high resolution, if you want, spatial resolution. So I will not go in detail, we just go on. So if you, just this is to show if you use instead of Samoza Plus, you use another retracker, so another one, which is this 640, you have still Samoza Plus, but this time you have 640 Hz. It's much more noisy, and then you have this gray line. So you have higher variability because it's due to the higher frequency, and the noise is much noise. In some places, it's very, very, very noisy. But you see that the form is all the same, so we are not doing something bad. Probably it's just another choice. If you use OCOG, which is the one that you normally also find in SMAP, is worse, and I still continue to prefer to use Samoza Plus. So here you see the way how we do now. Normally you have for each of the station you have the least standard deviation, and you look where it is. Yeah. So this in this case for Ottendorf I have 37 centimeters. That is quite nice. It is the nearest, the smallest. And they say this one is my accuracy. Okay. So in summary, we get less than 60 centimeters for all the stations. And of course, if you want to go in detail, but I will not go, you have also to study how many points you use and so on. But the message is that we have this result. This means that if we use, I choose the point where the standard deviation was the smallest, and the best result is obtained with fully focused SAR, 80 Hz, Samoza Plus. The other with Samoza Plus 20 Hz is also quite is the second good one. Yeah, so it's yeah. But okay, this one is the best. Not too bad. It's also the Samoza Plus with 20 Hz. And this is the result that we get at the end. So we have with unfocused SAMP, we have 0.62, and the other we had 0.46 if we do box plot over the 4 stations. This is what we get with this is just to show how the time series is in the point where that we selected. So it's good because in this case, for example, I use Samoza in the green one and the gray one. The gray is the tie gauge, and the other one, this one, is the one that gives the statistic that I showed. So now I am interested in high resolution spatial. and temporal if it's possible. So I wanted to show you that in Ottendorf, if this is the standard deviation that you know already, but this is the sea level anomaly at a given point in November 2018, and this is a track. So I will show you how it goes on in March. You see, it's quite different. All this is correctly for the tide. So we have or is a problem with the tides that was not eliminated. But I believe more that this could be a problem with the current, not a problem with the current. It's a real signal. So we have along the time, and also in other place, we have that this is in Bruce meter. We have a change in the form along the track. And this is something that we want really to see with altimetry, along track, fully focused, perfect. You can have alpha meter, but it's really doing this. So I have not yet checked with the model. I would like to check with the model that I have. We have a collaboration now with Novelties, which is producing a tidal model. So perhaps it will help us to understand this. And I heard that they are interested in having some place to look. So this is one of the first places they can look with the model that they are developing. So this is just to go on and to say simply that in every point that I have, this is almost a river, but it's with tide. I have, depending on the year, on the time of the year, I have a completely different shape. And it's kind the same in fully focus, in air console. So it's altimetry C already the same at the same point, different processing. So we will also probably also look to the waveform, what is the problem and so on. But this will be also an interesting part, but it's not what we want. Now we go on, and we go to the tide. So, I mean, this is a tidal river. Can we eliminate, how does our altimeter fit with the model? So we have a model that comes from Johanna Staneva, from Gerstach, I told. And the first time that I looked at the model, I was quite surprised because she didn't expect either, perhaps she didn't look. But the difference between the altimetry and my model, so no altimetry there, we switch on the tide gauge and the model, is alpha meter in most of the places. So probably there exist models which are better, but this model has also salinity, temperature, so is the dynamic model is not only height. So this means it's not fitting most the tide gauge. They are trying to reproduce the phenomena. So, and if I apply the T-tide, the correction of the tide from the tide, I get, and then I to both, and then I compare, I arrive to 20 centimeters. So there is still some difference between the model and the altimeter, so and the tide gauge. So we need a better model, or we tend to do something. Then last part of my talk is to look at, we'd like to find the discharge of the estuary, because it's important. We all want to know how much water goes to the sea, how the sea level is increased, and so on. This is the hydrodynamic model SLIM Shearms. And here you see also that, like in SWORD, they divide in part and so on. And for each part, they compute the tidal discharge, let's say. So the tidal the Elbe is a tidal system, so it has a maximum of 4 meter tide. And you have this, you have not only the discharge that comes from Gerstach, so the water, the fresh water, but you have also a tidal discharge that is the fact that it goes up and down due to the tide. So what we'd like to do with SWOT, it will be to analyze this region and to find the water, the tidal discharge from the space. Of course, the resolution, it will be not optimal, but we will try to do using this method here. That is a method that is called the method of curvature that was introduced by Mate. This is a colleague from Canada. And I have tried to apply this methodology. So in principle, it's very simple. So you have to compute the integral over a region that is, in my case, is the SWORD reaches. And I compute the increase in height in the region, the integral, and it will be, if you eliminate, you have to take into account that you have a discharge from the upper stream, And then, so the freshwater discharge, and then this will, the total will be everything that comes out in Ottendorf, so in the North Sea. So we did this, and we get a reasonable result. So the model has a little bit of spike, so we have to try to eliminate, but it's in good agreement with what we had, in the previous from the model. So this is just this
3 minutes.
model, and of course, together with Pascal, to try to sort the process, not the same conclusion of the model, and this will be something. So just to show that we try.
Luciana, you have 3 minutes.
Yeah, I finished. Just to show that we applied, we used a SWOT simulator with this model, and and this is what at the end we will find. We will have using SWOT. We'll have everywhere data. So here in principle the standard deviation, considering some error that we have, but and this is time series that we'll get at the So just to conclude, so what we did, what I tried to show is what another altimetry can now at the moment do in our estuary. So what we have done until now is to try to look at the high resolution along track, because we cannot do anything else with nadir altimetry. We have just a third track for Sentinel. 3, we have only one, also one for Sentinel-6, but what we want to do is really this high resolution to understand the phenomena and to improve the model. So model simulation is something that we are, our colleague Inga Stack will do with our data if it works. And seems that we will be able soon to try it with SWOT. Then we have fully focused, we have to understand, it's a very good new tool, but I think that in some place, like in the estuary, probably we will have something to work a little bit more to understand the signal and to work with the engineer that processes data to understand how to is the best way to do. Good that some of the plus can also be used there, and it gives the best result. So I am looking really forward to work with the device-wise SWOT mission using this method of Cubature, but also all other methods that are discussed also in these days. Thank you very much for your attention.
Thank you, Luciana. Any question? No? I have one question. Okay, so it's interesting because you are connecting the coastal ocean with the hydrology. So you know the two words are different. For example, how do you refer to compute the sea level anomaly? Means it's surface in the ocean, and then when you go inside the estuary and the river, which kind of reference?
This is I am I'm working on the here in the estuary also, but especially in the river. So in the river you have here you at the beginning you can use still the mean sea level, but then you have to use a reference that will be national normally. So you need to have a good geoid in order to especially if you are in a river, you need the geoid as a reference. Also because all the tide gauges are referred to this national reference that we have to transform. At the end, we will be in ETRF because we want to compare with Altimetry, but it's some processing in between.
Okay, thank you. Other questions? No? Okay, so we move to the next talk. Is from Ruiz Echeverri. She's going to talk about validation, use of altimetry products in the southwestern Atlantic continental shelf.
Hello, everyone. I will show today a result, like a summary of what our group is doing and has done. And also I would like to mention that some of the results that I'm showing are from master thesis from 2 girls that now they are in another institute. That's why I didn't put it here in the first slide, but I want to mention this. The motivation of this area, why we want to work here, is that the Southwest Antarctic continental shelf is one of the largest shelves in the world and hosts one of the most productive ecosystems. It's also characterized by large amplitudes that are bigger in the south and the amplitudes start getting lower in the north part of the region. And it also has a significant impact on balance in atmospheric CO2. However, the dynamic of the region related to the circulation and the sea level anomaly was in general studied by numerical models. Fortunately, our group, led by Martin Saraceno, put a lot of effort to trying to use altimetry data and validate this data, of course. So, as I said before, I want to summarize what we have done until now. The talk will be split in 3 sections: results, where I will start with the validation and its conclusion, and then the analysis of temporal variability of the sea level anomaly. And then I would like to say something about what we are doing now and future work. Knowing that the tidal amplitude in our region is really large and could be a really source of error in satellite correction, we decided to start analyzing the seasonal scale. So we selected the best 15 tide gauges along the shelf, and we selected the closest gridded satellite point to do the comparison. We obtained a root mean square of the difference lower than 2 centimeters. This is the bar of the root mean square, and the mean of this area is a root mean square of 0.6 centimeters. We also obtained high correlations above 0.8. And here on the left, on the right, I want to show 4 examples of these 4 stations where we easily see the good matching between gridded satellite altimetry and in situ data. However, we weren't content to only work it at seasonal scale or larger scale, and we tried to see the source of possible errors in altimetry data. So we started looking at the tidal models in an area that is this one, the River de la Plata history. We selected several models, regionals and global models, and we analyzed the amplitude and phase in 2 tide gauges, Palermo in the upper river and Ollarvide in the middle river. This one on the right is Palermo, this one is Ollarvide, and when we analyze the root sum square of these amplitudes and phases, we obtain that FES 2014 in both areas is the best model to represent the tide. However, when we see in this first blue bar on the amplitude in each station, we can see that especially in Palermo, the order of magnitude of the root sum square is similar to the amplitude. So we still need to work on this. Then we thinking about that the Rio La Plata estuary is really affected by the wind variability, we decided to take a look to the dynamical atmospheric correction. We selected the global model used for altimetry correction and 2 regional models. These are the map of the variance of the sea level anomaly due to the wind and pressure. And we can see that the global model is representing the spatial variability of the sea level, obtaining high values in the upper river and low values in the mouth of the river. However, when we look at the magnitude of this variance, we can see that the global model is underestimated what the regional models simulated. Here on the right, we have a time series of one example during 1993. What we can see in black, the model, the global model, and in blue, the tide gauge, and magenta line, the regional model, and we can see the difference in the magnitude. Then, thanks to the project, Franco-Argentina project CASIS, we were able to deploy a lot of instruments along JSON track 26 and along the latitude 44.7. Here we collected pressure, conductivity, temperature, and velocity data, and with the results and processing of this data, we generate a lot of results, and I will share some of them. As a part of master thesis of Dinora Garcia Santa Cruz, that now she's in Bremen, she analyzed the time models in all the shelf with the data collected during the campaigns and also from the tide catches. And she selected a 6 model in between globals and regional, and she split the region in 6 zones. And what she obtained is that the root mean square, the lowest root mean square, was obtained with the global FEST 2014 for the shelf area, for the shelf break, and also north of 42, while the regional model from Palma was the best option for the coast area and for the southern part of the shelf. Then Lorelei Lago, as a part of her PhD, she analyzed the along-shore transport in this area. And this here in this time series on the right, we have in black the satellite transport derived, along-shore transport along the derived from satellite data here, and in magenta line we have the in situ data that was calculated from direct ADCP data. And we can see that during this year, we have a good response between both time series, obtaining a correlation, significant correlation of 0.7 and a low root mean square of 0.6 SVEDRU. And this good matching was obtained for a temporal scale larger than 20 days. And this, what allowed us was to extend this period from 1 year to 25 years using gridded serial altimetry. Then Lorelei did a similar work here in the south for this sensor pressure and this ADCP. And you can see more detail about this in the poster downstairs. But what I want to show here is that here in the coast, when she analyzed the sea level in situ data, she found a high frequency variability that this spectrum that Aviso couldn't represent what the Mercator reanalysis model does. And here near the shelf, on the opposite, we obtain good correlation between trophic velocity derived from a long track data and in situ data for this the time series for periods larger than 10 days. As a master test, thanks to a national project, we were able to bought a bottom pressure recorder that we deployed under the nominal intersection of both of two JSON tracks, really close to the coast, almost 1 kilometer from the coast over here. And we analyzed not only the time model, but also the route tracking. Here I will start showing the comparison of the model. We have the tidal models, also regional and globals. This is the amplitude for the main components, and this is the phase. And when she analyzed the root sum square, we obtained that the regional model TPX is the best one, obtaining a root sum square lower than 5 centimeters. Being in a really coastal region, we decided to also analyze the route tracker. We look at the ALES route tracker and we compare it with the standard one, the MLE4. And when we constructed a time series over here, using both tracks and adding the best model and adding the ALES route tracker, we obtained that we have a correlation higher than 0.9 and a root mean square of 12 centimeters. And the good part of this comparison was also that we saw that the ALES route tracker recovered the 70% of the data. And we can see the statistic that we obtain when we use the standard correction, that especially when we can see the difference. Conclusion of this part is that the first 2014 tidal model is the best one for represent tide in our region, except the coast and sort of 42 and South Montia Gulf. Then that the global dynamic correction underestimate the sea level in the Rio de la Plata estuary, that the grids satellite data represent adequately the seasonal scales and also the transport, the current transport for periods larger than 20 days, and that the LSL tracker in the San Matias Gulf is very good for that area because we increased the number of valid data. After the validation result, we were excited to start looking at the physical of the sea level anomaly, and we start analyzing the seasonal scales. Here on the left, we have the annual amplitude derived from grid altimetry, and this is the annual amplitude derived from net heat flux. This represents the thermal component of the sea level anomaly, and look at the range is not the same bar scale, but what we can see is that the spatial pattern is quite similar south of 39, showing low amplitudes in the south and higher amplitudes in the north. If we do a lookup in this box, here is a time series of the altimetry data in blue, the magenta line, the static height derived from the net heat flux, and in black, the static height derived from situ data. We can see the good matching, corroborating that the sea level anomaly seasonal scale is due to this component. Something similar we did in the upper story of the upper continental shelf, applying empirical orthogonal function in the sea level anomaly. We obtained two modes. The first one explained the 65%, and we can see that there is a temporal variability that is quite similar to the one we obtained with the in situ data. And the second mode explains 33% that has a temporal variability similar to the wind. What we can see with this is that north of 39, the static height is still the dominant component, but we have a good influence from the wind. At interannual scale, we analyze this part of the shelf, and this time series on the left has the transport derived from grid altimetry in black, and in magenta, the reversed sum index. And we obtain a correlation of -5, and trying to understand which is the connection between those variables, we apply empirical orthogonal function in the CLA in this area. And we obtain three modes, and the first one, that is the most important, has this along-short gradient that will modulate the transport. And what is doing the sum is that will modulate the wind, and this wind, due to sum, will generate this cross-short gradient that, again, will expect to affect the transport in this area. Knowing that the sea level trends all around the world are not quite homogeneous, you have to look at the regional pattern. We decide to study the long-term trends in the area using altimetry data and analysis model. Here we have on the left the map of the 23 years of trends. We can see this the climate change initiative product, and this is the Copernicus product. We can see that all the shell is the sea level anomaly is increasing. And here on the right, we have the time series of the weighted area for the sea level anomaly and each component, mass change and static height. We can see in green the models, and in blue light, the light blue, the satellite, and we can see the trends that both coincide that the sea level is increasing, but the models is underestimating this rate. When we look at the components of the sea level trend, we can see that models and satellite data from GRACE in particular is showing also increasing a rate that is, you can see in the 13 years, a rate that is larger than we can obtain from the static height. So what we are seeing is that even though the model is underestimating the rate, satellite and models coincide that the mass change is the main contributor to sea level trends in this area.
2 minutes.
This one, you can also see these more details in the poster, but basically what I want to say for the intra-seasonal scale, the comparison between sea level anomaly and the meridian circulation in this ADCP station for periods lower than 19 days, we saw in these lagged correlation coefficient maps that there is a wave coming from Chile entering the south of the shelf and propagating within 3-4 days along the shelf. These waves, this rapid wave, the satellite altimetry couldn't capture, but we expect that with the SWOT data during the Calval period, we will do. Conclusion of this part is that the seasonal sea level is mainly dominated by the thermal component of the static height south of 39, while the interannual variability is dominated by the wind. At intraseasonal scale, we found with Mercator analysis that the CLA shows a presence of rapid waves, and their analysis model and satellite models data show that the sea level is increasing all over the region, mainly due to the mass change component. Ongoing work is we have Melina Martinez as a PhD student that she is looking at the high resolution temperature and salinity to estimate the static height and compare it with pre-analysis model and altimetry data. The idea is to understand what is the role of the static height in this area. The preliminary result shows that the static height is not the dominant component in this region. But also what we saw is that the model can represent this component quite good. We have here in magenta the in situ data, and in black the model, and then we also have the sea level anomaly of both model and altimetry data. And last slide that I want to show is a little bit of future work and ongoing work. We are part of the SWOT Adopt Crossover Consortium. And we are lucky that one of the SWOT paths will pass over the continental shelf. And we are preparing an oceanographic cruise right now for the end of February to deploy 4 instruments under the track, and with the idea to validate this data during the Calval period and also to understand the fine scale that interact with the biological activity. Thank you.
Okay, thank you. We have time for one question from the audience. No? No question?
I have a question. Your campaign you will do in February. What instrument you have there?
We have a DCP, sensor pressure, and 2 wire walkers that are coming from the I expect that it will be on time.
Yeah, and will last?
I don't know, because we are using Navy ships, so we are taking advantage of their path. So because I am trying to help in the logistic part, but I won't be on the campaign. So I don't know exactly how many days, but I know that for the deployment we need 2 days.
Yeah, because it's the Calval. Yeah. Thank you.
Okay, thank you. So now we have the next presentation from remote. Mulero Martinez going to talk about detecting coastal flow reversal over the Gulf of Cadiz using multi-mission altimetry data.
Good morning, everyone. Can you hear me?
Yes.
Okay, great. And can you see my presentation?
No, the presentation.
Yes.
Yes, it's there.
Yes.
You have to share. Okay.
Yeah, okay. You can see.
Yes, we can see it. Go ahead.
Yeah, okay, great. Well, good morning, everyone. Sorry for not being able to be there today. Today I'm presenting a section of my thesis, particularly focused on the capabilities of altimetry data for detecting coastal flow reversals over the Gulf of Cadiz. Starting with the study area, the study is focused on the Gulf of Cadiz, and particularly on the northernmost part of the Gulf. The surface circulation of the Gulf of Cadiz presents real complex dynamics regarding its temporal and spatial variability, mainly due to its location, since the area is characterized by water masses exchange through the Strait of Gibraltar, also the presence of eddies, fronts, several river mouths, and the main circulation is characterized by a bimodal circulation pattern. And here you can see the main features of such a bimodal pattern. There is a more detailed explanation of these two circulation modes. On the left side, you can see the name, so-called eastward mode, which is predominant under northwesterly conditions, which are also upwelling favorable conditions. And both the continental shelf circulation and the offshore circulation are east-bounded. On the right side, it is depicted the westward mode or coastal countercurrent mode. It is predominant during the upwelling relaxing periods. It's the same that, say, easterly wind periods. The main characteristic of this mode is the presence of a westward countercurrent opposed to the offshore eastward flow, as you can see in the scheme. Regarding some previous studies over the area with altimetry data, we published this work where we did an assessment of nearshore currents from using Cryosat-2, also in the Gulf of Cadiz, and compared that with high-frequency radar observations. We found some very good capacity of altimetry surface velocities for detecting small-scale gradients and structures over this complex area of variability, which is the Gulf of Cadiz. You can check that work with the code there. However, that from a practical or maybe more operational point of view, this work had some limitations since we only used tracks with an almost normal to the coast orientation, and the addition strategy for the altimetry data was not independent of the high frequency radar observation, since we use the scale of the spatial variability detected with the high frequency radar to select the filter length for the altimetry data addition strategy. So for the present study, we are doing something different to assess the possibilities of understanding the coastal circulation of the Gulf of Cadiz with altimetry data. Regarding the dataset use, we are using Sentinel-3A and 3B data over the Gulf of Cadiz. We are using level 2 data processed with the setup for coastal zones of the Salvatore processing service available in the PPRO platform. Moving to the addition strategy of the data that we are following, the sea level anomaly data is edited following some pre-existing methodologies, summarizing the following scheme. First, we remove values with bigger than 3 times the standard deviation using a 10 times loop. The resulting sea level anomaly is filtered with a locally weighted running line smoother or load filter. For this step, the cutoff window has been established at 30 kilometers, based both on the bibliography research and on an extensive evaluation against high-frequency radar measurements. Then the mean dynamic topography values interpolated to the track positions are added to the sea level anomaly to obtain the absolute dynamic topography values. And finally, through the use of the geostrophic approximation, we obtain normal to each point of the track absolute surface geostrophic current velocities. Well, in order to use that geostrophic approximation over shallow waters of the continental shelf, the Gulf of Cadiz, we have to consider for sure the bottom frictions. So we apply a correction for the bottom friction effect, applied as shown in the equation there. And you can also check the complete development of the equation and the correction in the study with the high frequency radar and cryosat that I have already mentioned. Well, here in this study, we compare ADCP data with the altimetry derived currents. For this, we use 72-hour average ADCP surface velocities previous to the corresponding satellite pass from the location from the ADCP deployments that you can see in the picture. Regarding the altimetry-based currents, we use the average along track velocities over the continental shelf up to 500 meters depth. And here you can see an example of the results with the comparison of altimetry data, the dots, and the ADCP data. We know and we assume that, of course, we are not measuring the same geophysical feature with the altimeter and the ADCP, but we wanted to check if we can, let's say, capture the coastal flow inversions. It is the alternance between the two circulation modes that I presented at the beginning. Using this simple statistic to tail feature test, we found that there's a significant relationship between the along-shore flow direction from ADCP and from the altimetry-based currents with a strong statistical p-value. So what it really means is that there is a significant relationship between the absolute dynamic topography, the cross-shore absolute dynamic topography gradient, and the coastal along-shore flow direction in the area. So from this, coming back to the circulation over the area, what we can say is that in general, when there is a lower sea level close to the shore and a higher sea level offshore, the along-shore geostrophic flow is eastward, this upwelling condition. And when the sea level is higher close to the coast, offshore, the coastal geostrophic flow goes westward. It is under relaxed upwelling conditions. So with this approach, we are currently doing a temporal analysis of the coastal circulation that allows to infer seasonal variability and gap-free along-shore flow reversals analysis, not depending just on the ADCP deployment. Besides, we are working on the wind component of the surface circulation and how it affects the main circulation over the area. Here you can see some preliminary results that show how strong is the wind effect over the circulation in the area, reaching up to reverse the coastal flow direction. So for sure, we have to consider the wind if we want to completely assess the circulation in the area. For this aim, we need a high resolution wind data source. So we have also validated the weather research and forecasting model over the area using wind speed from altimetry. So we can let's say, have a complete assessment of the circulation in the area using altimetry data from the validation of the wind model to the obtention of the geostrophic currents. Some preliminary results from the analysis of the seasonal variability, the upwelling and non-upwelling season over the area using both the bottom friction and the wind correction applied to the altimetry data. The results show that during the upwelling season, the coastal countercurrent is limited to the eastern basin, confined close to the coast due to the effect of the upwelling favorable westerly winds. And on the other hand, during non-upwelling seasons, the coastal countercurrent is completely developed up to the western basin due to the relaxation of the upwelling favorable winds and the presence of easterly winds. And this fact also agrees with the existence of a longshore pressure gradient contribution to the coastal circulation, which has also been proposed by several authors before. And well, from here, we can say those final remarks that current coastal altimetry data can be used to detect along-shore coastal flow reversals of the Gulf of Cardiff area, independently from any other observed system, like high-frequency radars, as has been statistically proven. Wind and bottom friction corrections play a critical role in obtaining realistic circulation results in the area when using altimetry data. We have to consider the both we've seen, and the preliminary results for the upwelling, non-upwelling seasonal variability agrees with previous studies in the area, as well as with the along-shore pressure gradient contribution to the coastal circulation. Thank you very much for your attention.
Okay, thank you. We have a time for questions. Okay. No questions? No? Okay, thank you for your presentation. And we can move to the last one. I invite my colleague, Francesco De Biasio, to take the floor. He's going to show the results from the work we are doing in a lagoon in the Northern Adriatic Sea using high resolution altimetry. Okay.
So, good morning to everyone. My name is Francesco De Biasio, and I'm going to present the study of the Marano Lagoon, Northern Adriatic Sea. This work has been done with Stefano Bindelli and the colleague Ron Abilea from JMKK. Well, few words about the motivation of the study. Coastal lagoons are shallow transition zones characterized by intertidal marches, shallow slow water flow, direct connection with the open sea, and partially shielded from the wind. There are about 32,000 lagoons around the world, identified along the 13% of the world's coastline. And in the Northern Adriatic Sea, there are two of them, which are the Marano and the Venice lagoons. And they are crossed by some tracks of Sentinel-3B and now also from one track of Sentinel-6. And they are vulnerable to changes of the water surface level due to storm surges and climate change. Because of the sparsity of the in situ measurements, especially in developing countries, the usage of satellite radar and LiDAR altimetry is currently the only option to monitor those changes. And a prominent role is taken in this context by the ongoing hydrocoastal project funded by the European Space Agency, aiming at generating a global satellite altimetry data set for exploiting in altimetry data in rivers, estuaries, lagoons, and the coastal zone. Okay, the map is depicting the situation and the position of the two lagoons in the northern Adriatic Sea. We see also the overimposed tracks of Sentinel-3 here in the Grado Lagoon, and in Venice there is this track crossing from the sea to the lagoon and passing by 4 different tide gauges. There is also the delta of the biggest Italian river, the Po, which has several centimetric crossing downstream. We have also available for the study ISA-SAT data over the Marano Lagoon. But they are not coincident, obviously, with the Sentinel-3 data. We use the Sentinel-3 radar altimetry data set over 3 years, and well, the radar altimetry processing involves 3 stages. First, we do the coherent sums of bars of the individual echoes. Then the radar range is estimated from the resulting signal. And finally, the range is translated to surface level. In our study, the ranges are derived from the Sentinel-3B raw echo waveforms using 2 methods. The first is the precise inland surface altimetry PISA algorithm. And the second is that of the ESA versatile altimetric toolkit of Ocean Research and Exploiting Salvatore from the Earth Console altimetry service of ESA, which and we use in particular the inland water high posting rate product, which is retracted with the Samosa Plus. Both data set are at 80 Hz, which means one observation every 89 meters. Differently from the Salvatore HPR product, the PISA algorithm identifies specular and quasi-specular echoes using the radar cross-sections and derives the range without any retracking. So yesterday we saw a presentation by Ron Abilea about possible anomaly in the waveforms of Sentinel-3B. And we can confirm that in Marano, the same anomaly pointed out by Ron is also present in the specular and quasi-specular data in the Marano Lagoon. You can see here the anomaly, which is given by the waveform not following the theoretical waveform expected for specular echoes. Okay, the first thing we noted in the Sentinel-3 Salvatore dataset is the presence of several outliers, both inside and outside the lagoon. So we decided not to remove those outliers and lead them into the dataset. Okay. Why specular echoes and how they are identified? They are identified by the PISA algorithm on the basis of the amplitude of their intensity. In particular, the specular echo are defined as having a peak greater than 100 decibel per square meter and a peak to side lobe spread of 37 decibel. While the quasi-specular have a lower threshold of 70 decibel per square meter and 20 decibel. So in this way, over the 3 years, in the lagoon, we have identified about 1,500 echoes divided in specular and quasi-specular. The analysis revealed that specular echo inside the lagoon and along the Ausa and Corno River, which are this little river here, which are just 50 to 100 meter wide, are visible, are detected, and also they are detected inside the lagoon. They are much more inside the lagoon, and they are preferably quasi-specular. Why specular echoes are so important? Because they have a much higher signal-to-noise ratio, and this translates to a more precise range. Go ahead. Another thing I have to say is that PISA strategy is only on detecting specular echoes, so it doesn't change anything of the ancillary information present in the original data set. So that all the other corrections used for the study are coming from the original Salvatore dataset. Okay, here you see some features that we have which were able to identify inside the Marano Lagoon. You see the maps. On the left, there is the track 384, and on the left, the 250. And superimposed, there are the surface levels determined with PISA. The color scale is on the right of the image. And you can see that the PISA classification recovers both specular and quasi-specular echoes. The specular are less than the quasi-specular. You can see also some little orange circles. They are mapping. They are marking the position of the pure specular burst. And we see that the quasi-specular echoes are seen to perform well also over some land areas like this one, and this one. We found that the signal from this land area, those fields, the range estimates are stable over the observation period, and they are consistent with the underlying topography. This zone are identified by the orange arrows. And we have also several echoes inside the narrow rivers, the Corno, the Hausa here, and the Corno here, and they are identified by the purple arrows. Well, we were curious about how those surfaces, those specular surfaces looks like. So we went for a survey in the Marano Lagoon. And during the survey, it turns out that there are 2 regions. You see them marked here, where the water flow is completely segregated from the mainstream of the lagoon. They are enclosed basins. One is a fish farm, and the other is a natural pool. And so we had to remove those points, those observations from the data set, because they were not describing a real sea level subject to tides, currents, etc. We also went for the survey to the fields where we had a signal from the land, and we were able to assess that the measurements made by the satellite was an effective one. It is real. We did it with a portable GPS. Well, at this point, we wanted to just understand the impact of the geophysical corrections in the data set. And here we see the time series of the 82 passes of the satellite over the lagoon. You see the sea level in blue here, and the tide gauge level during each pass marked by the black cross. And then we started to remove one correction at a time. The first one is the dynamic atmospheric correction, which is also mapped in blue at the same level of the crop. And then we removed also the ocean equilibrium tide, and we report here the original level without the dark and the ocean equilibrium tide in it. And then we did it for the same for the ocean long period tide. And finally, we removed also a part of the geocentric polar tide. And from this analysis, we understood that the astronomical tide is the first source contributing to the sea level variability, and the dynamic atmospheric correction was the second. And so we wanted to check how affordable is the astronomical tide modeled by FES inside the lagoon. We did it comparing the astronomical tide modeled by FES and derived by the UTide MATLAB package for the tide gauge in grado. We did it for 12 years, from 2010 to 2021, and found that the root mean square deviations of the level and the astronomical tide was in line. They differ by about 2 centimeters, so they are. Our conclusion is that FES can be used here to remove the tides from any point inside the lagoon with a good approximation. Another issue is the bathymetry, because bathymetry counts for the derivation of the astronomical tide, but we didn't understand which type of bathymetry FES is using. So this is an open issue to be understood. The first slide about comparison reports the scatter plot of the total water of the surface level versus the accumulated pass number. We have first the Salvatore HPR dataset, and then the values given by PISA, and the third, the ICES SAT2 passes over the same area during the same period. We see that Salvatore was able to recover all the 82 cycles. PISA instead performed a little lower with 75 cycles. And during this period, there were 17 cycles of ICES to compare with. We don't know here, we don't do any editing here. And we calculated the mean value of the sea level for each pass. So we compare the mean value of each pass surface levels with that of the tide gauge, and we obtained a root mean square deviation of 28 centimeters for Salvatore. Much better did Pisa instead with 8 centimeter, and the same 8 centimeter for RCS 2. Okay. Now there is another aspect of the comparison we made. Here we do the comparison with the same metrics, but using every individual observation. So we don't compute any average inside the pass, but we just put all the measurements as a time series and measure the mean square deviation and the mean absolute error. So we started from here. This is the how the sea level looks like offshore, taken measured by the Salvatore HPR. You can see that there are many outliers that have to be removed by statistical methods or in some other way. When we move from offshore to the lagoon, we see that the number of outliers is reduced, but there is still a remarkable noise. And finally, when we decided to keep only the Salvatore observation that were collocated with the Pisa one, so they are the measurements only over specular and quasi-specular surfaces, the situation is getting much better than before. And in this situation, we have a root mean square deviation with the tide gauge value of 14 centimeter for Salvatore and 9 centimeter for Pisa, and the mean absolute error is around the same 7 centimeters, which is a good result for us. And finally, I have another slide to show you about the performance, the precision of the two data set, burst to burst precision. Here we have the same plot with the same values, and just calculated the root mean square error and the mean absolute error of each time series by itself, just lagging the time series by one place, just to have an idea of how much was stable the measurement of the surface for each one of the two data set. Well, I have to say that many lagoons are engaged in the world, so the method can be replicated all over the world, and we can have altimetry measuring precisely the coastal sea level inside the lagoons. So, concluding remarks, overall, the results of the comparison are promising and will be revisited now with the novel hydrocoastal dataset, which is coming in the next few days. And we also remark that ESA-2 is another independent dataset that can be used to validate the radar altimetry products. And further analysis are necessary to investigate the physics of the echoes and how they relate to the surface types and wind conditions we have. Another remark is that specular echoes are less than normal echoes from the sea. So the question is if it is better to have a few precise measurements or many measurements of the lower precision. This is a question that has to be answered in the future. Specular and quasi-specular records are precious for the coastal altimetry. So our question is, could they be the key to exploiting the altimetry in the sheltered coastal regions like never before? And for this remark, we are going to propose the Marano Grado Lagoon as a Calval site for the Sentinel-3B and the Sentinel-6 and the ESA-2 missions as a laboratory where better understanding of radar reflectance at the sea is facilitated thanks to the existing infrastructures and logistics. Well, thank you.
Okay, thank you, Francesco. So one question.
I have a
question?
quick question. It's high time for a coffee break. On the site, you measured the level or just the roughness?
No, the level.
You went to measure level
Yes.
with a GPS? Maybe I didn't follow this.
We had a portable GPS, so we did just some sort of measurement of a difference between the place and all the story we had with the GPS going around the lagoon. And so we saw that more or less, I'm speaking about half a meter, the data were consistent. So we didn't have a professional method, just a very easy one with a GPS, a portable GPS.
Okay, next time you can go with a paddle or in the middle and get the sea level within a few centimeters.
Yeah.
Okay, but maybe I can help you with that. Next time you go, invite me.
Okay. Sure. Thank you.
So, question? No? Coffee break? What?
Yes, just if you're proposing that the lagoon is a Calval site, would you think there should be some additional instrumentation in situ?
Yeah, we have already some tight gauges which are operating since a long time, but for sure we need something collocated with the measurements. We were thinking about collocating some instruments in the crossover point of the two tracks.
But I guess it wouldn't be so good for waves.
Oh, yes, of course, for waves, for wind.
Okay.
Yeah. Thank you.
Okay, thank you.
Please go back to the slide in which you were showing results from ESA-2, Salvatore, and PISA, this one, right? So I was asking myself, in PISA, you just consider coherent or specular returns more. Yeah. In Salvatore, you consider all the looks, no? And that's why you have. So, okay. In the interface we offer for the Salvatore services, there is an option to allow you reducing the number of beams that you consider in multi-look in the stack. In a previous project we had named Crucial, there was also an investigation on the number of looks, and I think they just gave the message in the end that it's dependent on the scenario you're working on, that sometimes you obtain better results by reducing the amount of beams. So for usually in Salvatore we multi-look 180 beams. And I think in their case with Cryosat2 they obtain good results with 80 looks. Okay, taking this message in Salvatore there is an option to modify this value and you can get as low as 100 beams in the multi-look. So maybe in the future
we do some test also with the.
Thanks.
Thank you.
Very nice.
Okay, thank you. Jerome has an announcement.
Yeah. The people who intend to come with us tonight at the social event should go and pay and get your ticket. And the people who are not very convinced that they should join us, I would try to convince them to join us for two reasons. Because it's a social event, you should be with us. And I think we're going to have fun. And second is that we're in a little financial crisis because the people who registered are much more numerous than the people who intend to come. So I would encourage to come, especially if you said that you would come, because we have reserved the place for the number of people that registered. So please come, please go and pay and get your ticket. Thank you. Oh, yeah, the view is incredible. It's full moon. There's a lighthouse. We're going to have a drink on the terrace. It's going to be the moment you cannot miss for this coastal activity workshop in this beautiful city. So please, if you're undecided, please come with us. It would help also with the budget of the conference, of the workshop. Thank you.